Hello, everybody. My name is Brandon Wilson, and I'm here to talk about the end of forensics as we know it. Well, not really. That's overstating a little bit, but what I am going to talk about and hopefully get across is that USB storage devices are not as simple as they may seem. Forensic tools like write blockers may give the appearance that you can preserve and extract data from a device in a safe way, but they just simply cannot do that. So I'm going to take you through the thought process of how I and you would create a flash drive that self-destructs when they're accessed or even plugged in a way that we don't authorize. So first off, who here thought there was actually going to be a thumb drive explosion during this talk? No? Yes? No? Well, sorry. That's not going to happen. What is going to happen, though, is a discussion on what a flash drive actually is, what it isn't, how I learned more about it, and how it works, especially with little resources or help, some interesting things I found, and how we can all take advantage of them, and how we can protect ourselves against them. So what is a USB flash drive? Well, the answer is that it's not just a storage device, but it's a computer like any other. So it's complete with a processor, code for that processor to run, RAM for that code to utilize, and various forms of input and output, such as the USB controller so it can communicate with the computer, LEDs, so like little activity light on your flash drive, like when you're reading or writing data, it blinks at you, and the NAND memory flash chip, which is what actually holds all your data. USB is just the transport mechanism. It just enables the communication between the drive and a host computer. So just like an Ethernet cable networks computers together, this is just what links these two computers together. So how does a computer interact with a flash drive? Well, to answer that, we have to dig a little into how USB actually works. When a USB device is plugged into a host, the host's root hub detects that a device is connected, and then the host enumerates that device, which means it makes a series of standard requests asking it what kind of device it is. And these standard requests involve getting the device descriptor from the device as well as one or more configuration descriptors, each of which holds a series of interface descriptors. A device can choose to report itself as a custom vendor-specific device, or it can report itself as part of a standard device class, such as human interface devices, which is what keyboards and mice, joysticks, and all that are, or a Bluetooth device, like a USB Bluetooth adapter, or most importantly, mass storage devices, which is what flash drives, hard drives, even USB floppy drives are. And the way it reports these things is through class, subclass, and protocol IDs in either the device descriptor or, if it's not specified there, one of the interface descriptors within the configuration descriptor. Some IDs are reserved for specific device classes, such as human interface or mass storage device classes, or for custom vendor-specific devices. And the actual communication happens on specific one-way unidirectional pipes called endpoints, and the aforementioned descriptors define how many endpoints a device has, as well as what type each of them is, and in what direction data flows through them. So the host can send or receive a specific number of bytes on a particular endpoint, or the device can do it. And what happens beyond that is entirely device or class specific. So as I said, in our specific case, a flash drive falls under the mass storage device class, and that particular device class defines several different protocols, such as CBI or control bulk interrupt, which is used in USB floppy drives, or the one we'll be dealing with, the bulk only transport protocol, or BOT, which is used in pretty much everything else. Bulk only transport utilizes one bulk endpoint for incoming data and another bulk endpoint for outgoing data. So in this setup, the host always issues commands to the device, and the device responds. The device never volunteers data on its own. The host always initiates these requests. So a host initiates a request by sending what's called a CBW, or a command block wrapper, which consists of the command and sometimes a little extra data, kind of like parameters if necessary for that command. And then it enters the data phase where either the host sends more outgoing data to the device, or the device sends incoming data back to the host. And then it enters the final phase where the device sends back to the host a CSW, or a command status wrapper, which indicates the success or failure of that request. So what data is contained in these command and status wrappers? That's defined in the USB floppy interface, or UFI protocol. And it has floppy in the name because it was originally intended for floppy drives, but it's used for everything now. The UFI specification defines a subset of the SCSI command set, which contains all sorts of commands for getting the capabilities and capacity of a device, reading logical blocks or sectors, writing data to a logical block or sectors, all kinds of stuff. It's also very flexible in that you can define your own commands that get passed through this layer, which the specification defines as a vendor-specific command. And these commands make up the core of how we interact with USB storage devices. So as we'll see later on, these commands are extremely important. So if we open up a flash drive, we'll see all the core pieces. We see the USB port on the left, the NAND flash memory chip on the right, and then in between them we see a chip. And this chip is the brain of the whole system. It is responsible for communicating over USB and implementing all the aspects of that protocol that I just went over, as well as issuing commands to the NAND flash chip. So it's, in other words, it translates the requests to read or write logical blocks from the computer over USB, and then sends that to what the NAND memory chip needs to know in order to return or modify the requested data. And in this particular picture, you could see, hopefully you could see, it uses a chip made by Phison, Phison, which is a company you may have heard of before if you follow this kind of thing. If you recall all the bad USB stuff from a couple years ago, this is the chip that people focused on in order to implement so-called bad USB exploits. The code that this little chip runs can be upgraded without requiring a signature to verify that it's genuine and came from a trusted source. So since we know this chip can run code that we write, seems like a good target. So how in the world can we do that? Well, we can maybe fuzz the commands that are sent to it, see if we can figure out some kind of buffer overflow or some other kind of trick. I mean, we could do that, but that sounds really hard. Plus, I don't really know all that much about fuzzing, so we'll put that on the back burner. Another thing we could do is try to find the tools used to upgrade the firmware and then study how they work and then just duplicate what they do. It sounds promising, so we'll go with that. If we do some Googling about this kind of thing, we very quickly come across a Russian site called usbdev.ru, usbdev.ru. This site has everything. It has all sorts of information about USB flash drives, upgrading the firmware on them, reformatting them, leaked firmware images, the Chinese tools and utilities to flash them, everything. There are also a handful of English utilities intended for end users, the most important one being, in my opinion, the Patriot Memory Firmware Upgrade utility. It's for certain Patriot USB flash drives. These Chinese tools are, I don't know if you've ever messed with them, but they are very finicky. I had a lot of trouble trying to get these things to upgrade the firmware on a drive that I actually have, because they're highly configurable, but they're also very complex. And when the interface is partly in Chinese, it's hard to diagnose some of the more cryptic errors that it has. So these tools were useful in knowing what all should theoretically be possible with these drives, but getting them to actually do it is kind of a challenge. The one tool that doesn't throw any errors for me is called getinfo, and it just getinfo.exe. It just retrieves information from the drive, such as what firmware version it's currently on, what version of what utility flashed that version to it, how many partitions it has, what the name of the drive is, vendor product IDs, all that kind of stuff. As far as upgrading firmware, the one tool I could get to actually work was the one intended for end users, which is the Patriot Firmware utility, upgrade utility. To know what is happening over USB, we need to log that traffic somehow, though. And there are a bunch of options here. We can use one of a number of software analyzers. Some are Windows only, some work on Linux, and that works pretty well with most devices. We could fake the device using an Arduino or some other USB peripheral. So that means we would write code for that Arduino so that it would simulate a USB flash drive and then plug it in and then log the traffic that it receives from that firmware upgrade utility. You could even go so far as to add a USB host shield to it, so you could plug the actual flash drive into the Arduino and then just relay the traffic between the two and just log it somewhere and study it later. But that's really complicated, and that could be its own talk. I have done stuff like that before, but that's just overkill for this. So our final option is a hardware USB analyzer, like the Total Phase Beagle USB protocol analyzer here. I am fortunate enough to actually own one of these, so that's what I used. But the software one would have been fine. But this made my life a whole lot easier. Unfortunately, though, the one I have is the cheapest one you can get, which is not cheap, just the cheapest. And it can only log full speed or USB 1.1 traffic. So to get around that, I had to do what most people with this analyzer do. They hook up a self-powered USB 1.1 hub between it and the host, so it slows it down to full speed. That way you can log whatever traffic you want. And let me tell you, finding a self-powered hub, not a hub-powered one, so it has its own power supply. Finding a self-powered USB 1.1 hub is not easy these days, but I did find one, and so that's what I did. So we hook up the analyzer, the hub, the flash drive, and the PC, and we run our firmware update tool, the Patriot one, and this is what we get. Hopefully you can see that. But what we're looking at here is a traffic log between the PC and the USB flash drive. And you can see a series of outgoing packets in green and then incoming packets in blue going back and forth. And as I mentioned a little bit ago, a flash drive uses the mass storage device class. And since this is not a floppy drive, it uses the bulk-only transport protocol, which means it uses an incoming and outgoing bulk endpoint for communication back and forth. And it uses the UFI protocol, which is a subset of the SCSI command set. So basically, it wraps SCSI commands and their responses back and forth. So it's just SCSI commands, all we're talking about here. So you can see that the green outgoing packet that I've got highlighted starts out with bytes 55, 53, 42, and 43 in hex. Those are ASCII codes that correspond to U, S, B, and C, C being command, which means this is a CBW, or a command block wrapper, so it's wrapping the SCSI request. And after that follows a unique packet ID and some other junk, and then a packet length, which is in that highlighted row is 10 hex. And then the command byte is right after that. So here, that's a 6, 06. And 6, as it turns out, is a vendor-specific command. So it's reserved in the SCSI command set for the vendor or the manufacturer or whoever to use. And normally, you'd see something like 28, which means read sector, or 00, like what's highlighted, above what's highlighted. But since we have 06, that's a vendor-specific command. And the byte that follows the 06, which in the screenshot can be B3, 05, or B0, seems to be some sort of sub-command, if you will, that the Phison software uses to determine what we're really trying to do. So they use one command, and then all the data that they attach after that command is the actual command that it's going to work with, the action it's being told to do. So after that packet, we can see an incoming packet that starts with 55, 53, 42, 53, which is USB-S, S being status, which signifies the CSW, the command status wrapper, which is the end of the command. It's just the response to the success or failure response to that command. Sometimes there's data in between there, such as the long stream of incoming packets that you can see in the middle of that screenshot towards the bottom. And sometimes there's not. It just depends on the command. Some read data in, some send data out. And so the CBW indicates how much data is going to be in between there and in what direction it flows in. So to summarize this, what I discovered is a handful of commands, such as what drives that getinfo.exe utility, and then the basics of the firmware upgrade process. So to get basic information, we send the vendor-specific command 06, which is how all of these commands work, and then 0500 for one type of information, or 05 and then the word info for another type of information. What the difference is exactly, I'm not sure. I don't know. But to transfer some kind of block of data, we send an initial header using B1 to check to make sure that it worked with B0, and then 512 bytes at a time, we send the rest of the image with the address and the offset. There's some sort of image that gets sent across. So to do the actual firmware upgrade, we transfer the data using a certain couple of bytes. Then we send this unknown EE command. Don't know what that is. Then we transfer the data again using a different couple of bytes. Exact same data again. Then several more EE commands. Don't know what that is. But that's what we've observed so far. So what are these unknown chunks of data, these images that get transferred during the firmware upgrade? Well, obviously, at least one of them, part of it has to be the firmware data. So let's just reconstruct it from the traffic logs, which I did by hand, load it up in IDA Pro, and just find out. So and there's no way to know if that would work if it's compressed, encrypted, or obfuscated in some way, but it's worth a shot. We'll try it. So when I get to IDA Pro's processor selection window, where you choose what processor it is, I don't know what to pick, because I don't know what instructions that this Phison chip uses. Well, a little quick Googling, and Phison has a nice page on their own site that says what it is. It's an Intel 8051 CPU. Now, I had never seen 8051 assembly before this, but I did know assembly for several different processors, from x86 to Zlog or Zilog, Z80 to Motorola 68K. And I dabbled a little bit in ARM PowerPC, so I figured, you know one, you know them all, right? So I'll give it a shot. So I pick 8051, and I start analyzing it at address 0, I just assume it's at 0, and what I see actually seems to make sense. The 8051, like a lot of embedded CPUs, tend to have interrupt vectors and other stuff at the very beginning of memory. So we can see that IDA Pro, if you can see in the screenshot, has assumed the reset vector is at address 0. That's the first code that gets executed, which immediately jumps elsewhere. It's just a jump instruction. It jumps elsewhere in memory, which is typical. And then it seems to do a bunch of initialization things before it enters an infinite loop. That's exactly the kind of thing I would expect to see in an embedded device's OS or firmware. So that's great. We got a pretty good idea what's going on here. We can at least see some code. So the firmware upgrade traffic log revealed 2 different 8051 images. One of them, which is 32 kilobytes, looks pretty normal. Padded out to zeros at the end. That's what all the zeros are there. But the other one is around 241 kilobytes. Now, if you know anything about 8051, it only has one useful 16-bit register, which is the DPTR, or data pointer register. That means it can't address anything beyond 16 bits. So that's 64 kilobytes, because 65,535 is the largest 16-bit number. So in order to have a firmware image that's that large, 241 kilobytes, it has to be utilizing paging in some way. And if you aren't familiar with memory paging, that means it needs to split up the addressable 64 kilobyte range into pages or groups of memory. And then the firmware then swaps in whatever block of memory it needs at any given time to one of those pages. So all you have to do to access an address is access an address within that page, whatever you swapped in there. Now, some devices have additional hardware that do this paging for them, and some devices, like this one, do it through a combination of hardware and software. And I'll show you what I mean. Through playing around by loading different chunks of the firmware into different starting addresses in IDA Pro, because I don't know where this code's running from, so I'll just try things. But eventually I realized that the firmware is actually split up into a dozen or so different pages. The most important one being page 0 at the bottom there. That's the base page, which is fixed at address 0. And that base page is 16 kilobytes big, padded out to 16 kilobytes, from 0 all the way to 3FFF, leaving 4,000 upwards as another 32 kilobytes for swapping in different pages. Now there is code littered all over the place in the firmware that makes what I call off-page calls, or calls into subroutines that exist off on one of these other pages. So it passes the address of the function that it wants to call at the location it would exist if it were swapped in at 4,000 and up into a function that temporarily swaps in the page you wanted. It calls the code that you wanted, and then it restores whatever page was at 4,000 before you called it. So as an example, if I wanted to call a function at address 5,000 on page 1, I would set the data pointer register to 5,000, and then I would call the read-in page 1 function that you could see in the screenshot, which would swap in page 1, call the code at address 5,000, and then return back to another function that swaps in the original page, so it's like it never happened. Now, this raises some questions. First off, what is that function doing, and where is it getting the rest of the firmware from? And also, wherever the base page is stored, just what exactly is initially loading it at address 0? Well, as it turns out, this reveals some things about the boot process on this device. So we'll take a look at your typical boot on this thing. From the moment power is supplied to the device via the USB port, all it needs is power from the USB port, it needs to boot off something that's fixed in memory. So that means it must have some sort of read-only memory, some sort of boot ROM in the chip, built into the chip, that square chip. A fixed block of memory that can't be upgraded, can't be changed or anything. Now, the code stored on that boot ROM then becomes the very first thing to execute at address 0. So that code is responsible for communicating with the NAND flash chip and seeing if there's firmware stored on it for booting. So the firmware is actually stored on the NAND chip with your data. How it determines whether there's firmware there or not, I don't know. We don't have the code stored in the boot ROM. You can't see it. We just know that must be what it's doing, so we're just going to go with that assumption. Now, if there is firmware present, it loads the first 32 kilobytes of it to RAM at address 0. And then tells the chip to start booting from RAM instead of ROM. So normally the firmware runs from RAM. It just gets loaded from the NAND flash memory, the NAND flash chip into RAM and then runs from there. If there's not firmware present, then it just sits there and waits for code to be sent to it over USB, which means it has at least a tiny amount of code to communicate with the USB hardware and expose itself as a simple mass storage device without any media inserted so that the host could see it in order to send new firmware to it. So in a lot of these revelations, we can visit the USB traffic log from the firmware upgrade, and we can make a little more sense of the unknown commands. The first command that the host sends is BF, which causes the drive to disconnect and then reappear as a basic drive with no media present. So that is the boot ROM, which waits to receive more code to execute from RAM. So we send that small 32 kilobyte image I mentioned earlier to RAM and then send a B3 command. And that B3 command tells it to execute whatever we placed in RAM. So by that point, at this point, it's now running that small 32 kilobyte image. So then we send the large firmware image and then B3 again, which causes it to execute. So it was apparently necessary to be running this small 32 kilobyte image before we sent the firmware. It's reasonable to assume that this code is responsible for actually flashing or burning the firmware image that it's been receiving to the NAND chip. And that Russian usb-dev.ru site refers to this as the burner image, probably because it burns the firmware into the NAND. So it's great that we learned all this about the firmware on the drive, but what about actually modifying it? To do that, we need to write our own tools. So I did that originally in C#, but I wasn't exactly happy with that, especially since it's Windows only because it's C#. So I decided to rewrite it in Python, and I'm glad I did. It's much better now. Now, a word about cross-platform compatibility. Since the firmware upgrade process, and in fact any non-standard communication, happens over SCSI vendor-specific commands, I needed a cross-platform method of sending SCSI commands to attached USB devices. Now in Windows, that's like all the Chinese tools and on that site, that's how they do it. On Windows, that's very easy. It supports a SCSI, what's called a SCSI pass-through interface that allows you to send any command, even standard ones, to any storage device you specify. And on Linux, that's also easy. There's a IO CODL, IOCTL, however you prefer to say it, that allows you to send commands through its SCSI generic interface. But on OS X, you just can't. Not easily, anyway. There is one wacky way of doing it, but I didn't want to even try bothering with it. So instead, I implemented another way of communicating with it, with the USB device, and that's through libusb. The Python script also supports sending mass storage SCSI commands through the libusb, which will work on anything, Windows, Linux, and OS X. But that requires installing a libusb driver so you can communicate with it with libusb. And on Windows and Linux, that's cumbersome, so it just uses the OS's built-in SCSI interface. But on OS X, libusb is your only option. So if you use OS X and you want to use this, good luck. You'll have to unload the mass storage kernel driver, then install your own driver, and then use that libusb method, which theoretically works, but I don't know. So anyway, using these tools, I sent the original firmware to the drive, and it still works. So success, yay. But the real question is, can we modify it and send it? Well, we know we should be able to, but what should we try to modify? Well, let's take a look at what we could easily change and see the effects of it. Are there any hard-coded strings that we could change in the firmware? No, there's not. Not that I could see. What about crippling functionality in some kind of semi-safe way? Well, digging into the code that handles incoming USB data, we can find the equivalent of a case statement, which in assembly looks like this. It's a table of addresses and values, like in the bottom of the screenshot, where it deals with certain commands. So, for example, to handle SCSI command 03, which is requesting sense data, that you can see in that table, there's an address that EDE, it would jump there and handle it. Interestingly, despite the read and write sector commands, which I mentioned before was 28 and 2A, they are in that table, that case statement. But they're also explicitly checked for before we get there. So if you look up a little bit above that table, you can see it's doing an XOR with 28 and 2A. It's checking those commands explicitly. Now, I don't know why it's doing that. It's probably to speed up execution when you're reading or writing sectors. But if we were to patch the 2A value in that code that it's XORing, as well as the 2A in the table to something nonsensical like F1, then the drive will no longer have the ability to respond to write sector requests. So I did that, and as you might expect, it does work. So now that drive can't write to its NAND chip. So it's a read-only drive now. So we know we're able to modify the firmware successfully since we know we can do that. But what happens when we do something dangerous and screw up the firmware so badly that it can't even boot or get to the point where it will accept new firmware, which I can tell you I did many, many, many times. What do you do in that situation? Well, if you recall, during the boot process, when we first plug the drive in and supply power to it through USB, it executes the code on the boot ROM. And then, if it can detect valid firmware on the NAND chip, it copies it to RAM and transfers control to it. So if we disrupt that process, it'll enter what that Russian site refers to as test mode, which is what we've been calling the boot ROM, where we'll be able to transfer new firmware to it. So how do we disrupt that process? You disrupt the ability to communicate with the NAND chip. So if we take a look at the data sheet and pinout online, also on the Russian site, can't tell you how useful that site is, we could find a couple of pins next to each other that are tied to the NAND data pins. So if we short, that's how the chip communicate. That's how the NAND chip communicates with that Phison chip to read or write data on it. So if we short those pins together, there's no way the controller can communicate with that memory chip. So no communication means no firmware, which means we're in test mode. And from here, we can just use our tools to flash it as normal. Now, it's difficult to hold something really tiny and metal on two very specific tiny pins while trying to plug the drive into the USB port all at the same time. So I came up with a quick reset cable, which is just a switch. It's just a USB extension cable with a switch on the 5-volt line. That way I could short the pins with one hand and then just flick the switch with the other one. That's so I don't have to plug it in, it's already plugged in. And that's the same as inserting it into the USB port. So I had to do that so many times, so I got really frustrated, so I made that thing. So now that we have a super basic understanding of how the firmware works and how to go about making patches to it, now we can finally get to decide what we want to do. So if you've seen all the bad USB talk from a while back, you may have seen some of these patches before. We can create hidden partitions by changing the SCSI response code to only return half the capacity of the drive. Whatever it would normally return, we just cut it in half. We just patch the firmware to cut it in half and return that instead. And either leave the read sector command alone or change it to double the sector that it's going to be writing to, the LBA or logical block address. So while the user and the OS thinks that they're modifying the entire drive and see the entire drive, they really only see half of it and they're only manipulating half of it. So there's an entire half of the NAND chip they can't even see. So we can change the way that command works and it won't be obvious to any software that exists today. Or since the firmware is really complicated. It has built-in password protection functionality. It even has some basic encryption stuff in there, all kinds of stuff. So we could cripple it to always use the same password. So if the user tries to set ABC, we really store DEF. So, their password becomes useless at that point. Or we could send raw NAND chip commands ourselves, such as getting the chip ID or the NAND chip ID, reading pages or ECC data, or writing to it, or erasing it. So maybe we can do some damage with this. So now we finally get to the self-destructing drive patch, firmware patch. So what we can do is patch the firmware to start off in a so-called locked state. So we would have to unlock it via a special command that we just make up and create before it will indicate that there's any media present or any read sector requests succeed. So we'll also we'll add a counter. Since normally we'd have like a timer, but since we don't know anything about the timer hardware in this thing, we'll just use a counter. Kind of go old school with it and just use a counter. So we'll have a counter that keeps incrementing over and over, which can only be reset via a command that we send it. So only we know what command to send to reset it. Otherwise, it just keeps on ticking up. And when that counter reaches a certain point, say several seconds worth of inactivity, the drive will just lock up and erase the area of the NAND chip that holds the firmware, as well as everything else on the NAND chip, and just wait for the user to realize how screwed they are. So the net effect of this is that if anyone plugs the drive or even supplies power to it, you can plug it into a cigarette lighter adapter, anything. Without plugging it into a computer that keeps sending that counter reset command over and over, the drive will kill itself within a matter of seconds. So in fact, unless you send that special command to unlock it, you can't even access the data on it anyway. So to implement this idea, there are a whole bunch of things we need to do. We need to keep track of this locked versus unlocked state and the potentially very large, because we don't know how big it needs to be, this very large counter value. So we're going to need to steal some bytes from the RAM on the chip. And we're also going to need to patch the initialization code that runs at the very start of the firmware to set the initial values of these RAM bytes. Started at 0, started at locked. So we're going to need to patch. We're also going to need to patch the infinite loop that it runs in over and over while it checks to see if there's any USB data it needs to deal with, any SCSI commands it needs to deal with. We're going to need to patch that infinite loop to increment the counter if it's unlocked. So it doesn't do anything if it's locked, but as soon as it becomes unlocked, it starts incrementing that counter over and over again. And if we hit whatever threshold equates to a few seconds of inactivity, then we disable all interrupts, issue the raw erase commands to the NAND chip to erase the firmware and everything else on it, and just lock up. Just spin in an infinite loop over and over again. a counter is probably not the best thing to do, but like I said, it's kind of old school. But since it's safe to assume the speed of this process is probably constant, a counter to track the passage of time is probably okay. So that's what we'll go with. We're also going to need to patch in SCSI vendor commands to set the unlocked flag and to reset that counter back to 0. So we're going to need to patch the request since command that's the command that the computer uses to figure out if there's any media inserted or not. Like for a floppy drive, you don't have a floppy in the drive, it returns no media present. So we'll patch the request since command, the handling of it, to return no media present if that flag says that we're still locked. And we're also going to want to patch the read sector command to do the same thing, just in case some wise guy doesn't believe the sense data and tries to read it anyway by sending the read sector command regardless of what the sense data says. So, stealing bytes from RAM. We have no idea what RAM areas the firmware is coded to use, but we do know that it doesn't modify itself, particularly page 0, since that never changes. It's at address 0. It needs to be there in order to do all this page swapping madness. So it's the area from 4000 onward that the page swapping code uses to swap in different pages of code. So it's probably okay to steal a few bytes from the end of page 0. So right around 3FF0, right before 4000, it's probably okay to steal those. So the patching calls to those subroutines, we're gonna need to find a section that's at least 3 bytes big, since that's how big an 8051 call instruction is, and replace it with a call to our code way towards the end of page 0. We're going to patch our code in there as well. Or we could patch it somewhere else, but page 0 is easiest. Any leftover bytes from instructions that we partially overwrote with that call instruction, we can just replace them with zeros, which in 8051 is a NOP or no op or no operation instruction. It just does nothing, which if you've patched anything, you got to have an op instruction or something that does nothing. Then our own code could do, at the end of page 0, it can do whatever the firmware originally did and that we overwrote, in addition to whatever we needed it to do in the first place. So this is great. We finally have ourselves a self-destructing drive, but theoretically, all a person would have to do is get a hold of the Python or whatever computer script that sends that unlock and counter reset commands and just run that on their own computer. So then they're free to run whatever kind of forensic analysis they want. That's true, but it is as simple as sending a counter reset command. But what if we made that command more complicated, like sending a password in the command? You could do that, but then that packet would be vulnerable to USB traffic sniffing, which you can even do remotely in software. So that's probably not the best thing to do. So now what? We could scramble the traffic between the host and the PC, so that if you're looking at it in an analyzer, you don't know what's going on. It's a separate side discussion. How many here have heard of Disney Infinity, a game for, overpriced game with all the toys? Yeah. It's a game released for pretty much every console that comes with this USB portal that you plug into the console, and you buy a ton of expensive RFID toys for your kids to place on it. And then when you do, the game recognizes that it's a character. It recognizes that you placed a character on it and lets you play as that character in the game. Well, to prevent people from emulating that USB portal with an Arduino or something and just never buy any of the figures, Disney came up with this scheme where both the console and the portal had to keep generating the same random numbers based on a shared seed that they both knew and decided at runtime. And if they ever got out of sync, the game would just stop talking to the portal. So the console would generate a random seed, scramble it so you couldn't tell what was in the USB traffic logs, and then send that to the portal. So the portal would then descramble that and use the seed to generate its own random numbers. And then it would generate the next random number, and it'd send it scrambled back to the console. And so the console would do the same thing. It would generate its own random number. And if what it came up with didn't match the random number that the portal sent, it would just freak out and stop talking to it. Just assume it's a fake and just stop talking to it. Well, we can do that same kind of logic here. So if we did that, we could prevent USB traffic sniffing, but it would only work well if the drive is the only one that could descramble the traffic. The big problem with all this is, what if the attacker never plugs the drive in, which is what you should do if you're dealing with this kind of drive, and instead dumps the entire contents of the NAND chip, which would give them access to the data as it sits and the firmware. So then they could just disassemble and figure out our scrambling algorithm or passphrase or whatever it is that we try to do to protect it. And then they'd be able to do the same thing. Well, okay, fine. So we'll patch the firmware so that whenever a read or write sector command comes in, we'll just encrypt or decrypt the contents of the USB data buffer before it passes it along to the NAND chip. But that raises the question, where would the encryption key be? Because if you stored it in the firmware, then all they have to do is dump the firmware, and then they got their key, so that's useless. So instead of storing it in firmware, you could have the firmware derive it based on a password or something sent to it by the PC side, counter resetting script. The point is, this whole cat and mouse game could just go on forever. It can get as complicated as you want or need it to be. So it's kind of, it's just a cat and mouse thing. No demo, sorry to say. I ran out of time, couldn't scramble one together for you. But I have a nice graphic. It's almost as good. Right? Here are some links to the GitHub repository that holds the original C# bad USB code that I wrote, the new Python code, that's the third link there, the Russian site specific to the Phison USB controller that I've been talking about, and then at the bottom, a repository of code that has a from-scratch implementation of firmware for one particular version of these controllers, these Phison controllers. And it also has a technical wiki for writing 8051 code for this thing. It's got a lot of documentation about all the registers and all the memory mapped I/O and all the stuff that you would need to know to write code for this thing, which can be really helpful. So in conclusion, a flash drive is not just a storage device. It's really not all that different from your host computer. And USB is nothing more than a transport mechanism connecting the two together. So you can't trust a flash drive any more than you can trust another computer on a network. The moment you supply power to a device by plugging it in, you're taking a risk. Not only a risk for your computer, but a risk for anything about the state of that device that you might care about, such as what's currently stored on it. So I promise you, everything I just stood up here and talked about, there are people in this world that are doing it already. It's out there. So it's not just theoretical. And if you truly care about retrieving the data from something, don't plug it in. Write blockers are not good enough. All it does is block the computer from sending the command. The flash drive can do whatever it wants. If it's got power, it can do anything. So hopefully this talk educated and entertained a little bit. I put up a few ways to contact or follow me if you're interested. And thanks for your time. Appreciate it.